Hello and welcome to a presentation entitled The Mixing Problems. Here I'm going to give you one example of popular problems called the mixing problems. These are problems which are applicable to the real world of work in the chemical industry. I think in our previous discussion, in our first presentation, where I introduced differential equations and motivated why we should do differential equations, I presented you different models where differential equations were used, and one of them was about this mixing problem, whereby if we've got a tank like this where inside the tank there's a certain amount of liquid, or let's say water in this case, and we pump in a certain concentration of let's say something like salt, and they pump out, obviously pumping out a different concentration of salt here, but at a constant flow rate. We arrived at the fact that if we denote A of T as the amount of salt at any time T, then the rate of change of the amount of salt in the solution here is dA dt is equal to flow in rate multiplied by the concentration of salt in this case minus the flow out rate multiplied by the concentration. In this case, the concentration will be given by AT divided by the volume of the, the tank. And then this actually shapes up a differential equation, which we are actually going to give an example of how to solve it. And it actually turns out these types of equations are of separable variables. So in this case, I'm giving you one more example of application of equations of separable variables. So let's turn to the problem, which reads as follows. This is mixing problem modeling with separable ordinary differential equations. So what are given here, we're given a tank, like we've seen, which contains 4,000 liters of water, and in that 4,000 liters is containing 50 kgs of salt dissolved in it. So in this case, what we can say that if we denote our amount of salt in the tank as A of T, so what we're told in the first line here is that the initial amount of salt in this case, which is A at time T equal to 0, is simply equals to 50 kgs. I'll just write 50 there and forget about the units for now. And then it says brine. Now it's another solution which is of salt, which is pumped in here, is pumped in at 40 liters per minute, and the salt contained there is 2.5 kgs. So the amount of salt there in that case, we've got 40 liters multiplied by 2.5, and I hope you can see that this will give you like 100 kgs of salt. And then on the other hand, we're told also that this salt solution is kept uniform, is well mixed by stirring, and the solution is pumped out at a similar rate of 40 liters per minute. So what we get here is what we've got here is the flow-in rate, and the flow-out rate is 40 liters per minute. So in this case, according to what we've seen there, we would then multiply the flow out, it will be 40 divided by the total volume of, that's the concentration, 40 divided by the total volume of 4,000 multiplied by 80. So now, following our differential equation now, then we would say the rate of change of the amount of salt with respect to time will be equal to the flow in rate, which is 40 liters per minute, multiplied by the concentration, which is 2.5, minus then the flow out rate, which is 40 again, multiplied by the concentration, which is simply A over the volume, which is 4,000 liters. Then at this point, we've got a differential equation which we must solve. Let's simplify this as follows. This will simplify, then we saw already that this give us 100 minus, if we simplify here, I hope you can see that we're going to get a over 100. Simplify the zeros, then you got 4 there, divide that, you get the denominator by 4, you get 100. So you got here as a over 100. Written in simplest form here, we can simply write this as 100 minus 0.01a. In this case, we're in the presence of a differential which says dA dt equals to 100 minus 0.01a. Now, for convenience, what we're going to do here now, this right hand side, let's factorize it, and taking out a common factor 0.1, which will simply be look at like 0.01 in brackets. Then in this case, when you're taking out common factor 0.1, you have to divide this 100 by 0.01, which I suppose is going to give you 10,000, then minus a, that's that. So in short, you've got a differential equation which is dA dt is equals to 0.01, 10,000 minus a. And then we recognize that this is an equation of separable variables. So we now need to separate variables. We can simply separate variables here by multiplying both sides of the equation by dt over 10,000 minus a. Doing that, what we get dA over 10,000 minus a equals to 0.01 dt. Now at this stage, what we need to do, we simply need now to evoke direct integration on both sides, which will now have, we have this as dA over 10,000 minus a equals to the integral of 0.01. Now integrating here, what we can see here is that we've got a derivative here of ln form. In other words, the derivative of the denominator here is just dA, the differentiating equals to a. So, which in this case, this will integrate as ln absolute value of 10,000 minus a equals to, here this is what integrating a constant, which is basically a derivative of a linear function. Then this will come up as 0.01 t plus c1. Now, I think we're done with integration. So now what we've got to do now, we've got to find a way of expressing a of t. Now it's expressing a as a function, an explicit function of t. So what we can do now here, we can apply, sorry, there's something missing here. The derivative of this is minus 1, so we need to divide both this side of the integral by minus 1, which will give us minus ln that. I hope you note that very well. So having this minus 1 here, what I'm going to do now, at this point when we're done with our integration here, we need to get rid of this minus sign here, conveniently by multiplying both sides by minus 1. So multiplying there, we're going to get ln of 10,000 minus a equals to minus 0.01 t plus c. So now remember, our target is to get a of t as a subject formula. Now let's express a as a explicit function of t. So what we can do now here, we can apply e on both sides, which is inverse to ln, and we've got here e to the power ln of 10,000 minus a in absolute value equals to e to the power minus 0.01 t plus c1. I want to use brackets there to emphasize that the whole of this sum becomes the power of e. And now applying rules of exponents here, you see clearly that we're going to have e to the power minus 0.01 t multiplied by e to the power c1. And then we can now set e to the power c1 equals to c2. And then rewriting this, the left hand side would simply be absolute value of 10,000 minus A equals to C2 multiplied by E to the power minus 0.01 T. So then at this point, I think we're now ready to remove the bracket, the absolute value here, whereby we're going to leave this as 10,000 minus A equals to plus or minus C2 e to the power minus 0.01. Remember, when we are putting absolute value there, we normally get a positive quantity ignoring the sign. So when you remove it, this is the reason why I'm putting a plus or minus C2 here. So then the next thing now, our target is leave A subject to the formula. Then what we're going to do here, we're going to add minus 10,000 on both sides, which is going to give us minus A on the left hand side equals to minus 10,000 plus or minus C2 e to the power minus 0.01 T. And then I think our last step here now to get A, we'll simply need again to multiply by minus 1 on both sides, which would give us A, which you can immediately now express it as a function of T. A equals to 10,000. And then if we multiply by minus, this is an arbitrary constant, we actually get another constant, which we can just simply write this as C e to the power minus 0.01 T. Because I'm multiplying this plus or minus C by minus, and the C2 is a constant, so I'll simply get another constant which I can call C here, which is not really a problem. So then at this point now, we must now go back to what we know to determine this C, because we need a unique solution if we're going to be able to evaluate this function after 1 hour. So we should remember that we started with A at 0 being equals to 50, which means that if this expression is evaluated as 0, we're going to get 50. So we've got here 10,000 plus C times 1, because e to the power 0 will be 1. Then this, I think you can see that it simply gives us a conclusion that C is equals to 50 minus 10,000, which will give us minus 9,950. So in that case, our unique solution after using the initial conditions is simply 80 equals to 10,000 minus 9,950 e to the power minus 0.01 T. So that will be the function modeling the amount of salt in the tank. Now, our second question was compute approximately the amount of salt after 1 hour. We must take note that the flow rates here were given per minute. So after 1 hour, we're talking about 60 minutes, which means we must evaluate this function at 60 minutes. So this is the function we've got here. So to find out how much salt is there after 1 hour, so we have to say A at 60, which is going to be equals to 10,000 minus 9,950 multiplied by E to the power minus 0.01 multiplied by 60. That should be the value of that function. So I think at that point, because of this value, you definitely need to use your calculator. Let's see what the calculator gives us. I've already entered the value before, which is here 10,000 minus 9,950 times e to the power minus 0.01 times 60. That's what it gets. So that it gives us 4,539.32, and this will be kilograms. So that's why. And clearly we can see that this function is increasing because check what's happening here. We are continuously separating a smaller and smaller value from 10,000, which means the difference actually here will be growing. And we know that the initial value, remember, it was 50 kgs, and now after 1 hour is already this amount. So then the next question was we needed to sketch the graph of the solution so that we can give an accurate interpretation of what is happening. I will illustrate graphically what is happening with the amount of salt in that solution. So then we'll get a graph like this because of what we've said. For the initial value will be 50, and because we're subtracting smaller and smaller value, so this function is increasing, and but it will never go beyond beyond the 10,000, because remember this exponential decay here will never be 0 or less than 0. So the graph will grow asymptotically to this horizontal line here, which is A is equal to 10,000. I hope that is clear. So in this case, I think the solution has been done. It's clear what we are supposed to do. So what you can now do is to really look at it and make sure that you master all the things which you said here, and then go to your text and the recommended text and get further examples to practice this. Otherwise, I'm not going to give another example similar to this, but you can look at similar examples sometimes where you maybe are mixing alcohol with some other water and whatever, or another situation where you could be just flushing out the tank in a situation where we just pump pure water in the tank, which had a solution, and the pumping out at another rate. You will see again that you get a similar problem where you apply equations of separable variables. Otherwise, at this point, I would like to say thank you for listening. My name is Charles Suasfani Msipa.